Hello friends, and welcome to yet another lecture on chemical engineering thermodynamics. We all are aware of the Maxwell's equations or the Maxwell's relations. On your screen is the Maxwell's relations. Today we will be studying about Joule-Thomson coefficient. As I told you that today we will be studying about Joule-Thomson effect. For a real gas, enthalpy is nothing but a function of temperature and pressure. It should be noted that for any pure real gas, fixing two variables fixes its state. That is, it fixes all the other state variables. Therefore, for a real gas, if we fix the temperature and pressure, it fixes the enthalpy. So, enthalpy is nothing but a function of temperature and pressure. Now, we differentiate this equation and we get dou H by dou T at P dt plus dou H by dou P at T dP. For a constant enthalpy process, the LHS will be 0. We now rewrite this equation as dou T by dou P. We can take this part of the equation, take it to the LHS and get dou T by dou P as one of the terms. Dou H by dou T is nothing but Cp. Therefore, after rearrangement, we get dou T by dou P at H is equal to minus 1 upon Cp dou H by dou P at T. The Joule-Thomson's coefficient is nothing but mu Jt, which is defined as dou T by dou P at constant enthalpy. From the equation, dH is equal to T ds plus V dP at constant temperature, we get dou H by dou P at T is equal to T dou S by dou P at T plus V. Now we have a replacement for dou H by dou P in this equation, but we still do not know how would we calculate dou S by dou P for a real gas. The Maxwell's relations come to our aid. From the Maxwell's relation, we have dou S by dou P at T is equal to minus dou V by dou T at P. Now we replace this and we get dou H by dou P is equal to minus T dou V by dou T at P plus V. Now we replace this and we get the Joule-Thomson's coefficient as minus V minus T dou V by dou T at P upon Cp. Now let's calculate the Joule-Thomson's coefficient for hydrogen and nitrogen at 50 bar and 25 degrees Celsius, assuming that they are van der Waals gas. And this is a good assumption because both of these gases are close to ideal gases and they deviate slightly from ideal gases. So van der Waals equation of state is a very good representation of their superheated state. Now, what we can do is we can open a workbook in Maxima. The workbook is already ready, so I shall demonstrate it. There goes the demonstration. The van der Waals equation of state is P is equal to 8.314, that is R into T over V minus A upon V square. So this is the van der Waals equation of state. Now we first calculate the Joule-Thomson coefficient for hydrogen. Now the pressure, critical pressure and the critical temperature for hydrogen are 1313 kilopascals and 19.33 Kelvin. We calculate the value of A and B for hydrogen, replace it in the van der Waals equation. Further, we calculate an expression for Joule Thomson's coefficient for van der Waals gas, and we get the following expression. Now, we calculate the volume for hydrogen at 50 bar and 293 Kelvin. I would like to make a slight correction here that if it is 25 degrees Celsius, it should be 298 Kelvin. Fine. So let's run this. Yes. Now we go back. So this is the expression for the Joule Thomson's coefficient. Now for a pressure of 50 bar and 298 Kelvin, we calculate the volume of hydrogen. 0.5076 is the volume. So 0.5076, I have made a note here. Now I replace the volume, the temperature, the A and the B in the Joule Thomson coefficient expression, and I calculate it. And what do I get? It is minus 3.14 into 10 raised to minus 4. Now, this is very interesting to note. We all have been told that whenever we throttle any gas, throttling is a isenthalpic process. When you take a gas, pass it through a valve, and it comes out from the other side of the valve, it cools down. This is known as Joule Thomson's expansion. We all have been taught mostly that in Joule Thomson's expansion, the gas cools down. But what we find here is something interesting, that for hydrogen, it actually heats up, which is a fact. Therefore, if you have hydrogen in a pressurized tank and the pressurized tank suddenly leaks, hydrogen after leaking will have a tendency to explode because its temperature rises. Now let's calculate the Joule Thomson's coefficient for nitrogen. We note the values of the critical temperature and pressure. We also calculate the values of A and B. We calculate the volume for nitrogen gas at 50 bar and 298 Kelvin, and we get 0.4819 as the volume. And what do we find? That the Joule Thomson's coefficient is 0.0048. It's a positive value. So we can say that when nitrogen is throttled, it will cool down. Or if nitrogen is held in a container and if the container suddenly leaks or develops a leak, the nitrogen will cool down when it comes out of the leak. Therefore, this was a mathematical demonstration on how to calculate the Joule Thomson's coefficient for any gas using van der Waals equation. So friends, that was the end of the lecture. Hope you enjoyed the lecture and hope it was informative to you. Please subscribe my channel. Your subscription motivates me to make more videos which are relevant to people desirous of studying thermodynamics. If you have any topic in mind on which you want a lecture, do write it in the comments. I'll try my best to make lectures on those topics. I hope my lecture was clear, and once again, don't forget to subscribe. Have a great day. Bye.